Observe this generated subject. At frame 1, the anatomy is precise and the lighting is photorealistic. By frame 24, the physics have failed. The limbs melt and the face dissolves into chaotic, unpredictable shapes. When we freeze the action to analyze the collapse, we see a failure of geometric boundaries. The model has lost the mathematical coordinates of the subject. Diffusion models are optimized for static aesthetics, meaning they can represent a single moment perfectly while struggling to maintain that logic across a sequence. During generation, the model attempts to predict the trajectory of pixels across time without a spatial anchor, leading to the distortion seen here. Stabilizing this motion requires a shift away from text-based prompting toward structural lock, a method of rigid geometric conditioning. Without a structural lock, the model produces aesthetic guesses rather than a spatially consistent render. A common reaction to this instability is to add increasingly complex negative text prompts, attempting to verbally command the model to maintain the subject's shape. This fails because of how cross-attention functions, the layer where text instructions interact with image generation. In this 2D pixel grid, instructional vectors define what to draw, but not where those pixels belong. They highlight broad clusters, not sharp borders. When cascaded along the z-axis, the vectors scatter randomly. There is no mathematical memory connecting frames. Consequently, the model may completely forget the exact boundary of a subject's arm between millisecond 0 and millisecond 33. Semantic text control alone cannot enforce physics. It fundamentally lacks the necessary data to solve spatial geometry problems over time. To find a solution, we move into the latent space, the mathematical environment where diffusion occurs. Here, frame 1 is represented by a single, tightly clustered coordinate. Standard diffusion creates this coordinate by denoising random noise into a specific data cluster. To create video, the model must generate subsequent coordinates for frames 2, 3, and 4. This reveals the root of the problem, latent drift. Without constraints, these frame coordinates wander away from the original subject's identity, forming a chaotic cloud instead of a linear path. This mathematical scattering in the latent space is what manifests as morphing limbs in the final video. Latent drift is the mathematical representation of physical matter losing its consistency. This drift is a byproduct of the processing architecture, the 2D U-Net. Standard diffusion models process images as flat data. They have no native comprehension of a sequence. For video, we must force the model to denoise an entire sequence simultaneously, adding a temporal z-axis to its processing. Temporal attention layers bridge this gap. As the spatial layers separate, perpendicular bridging lines connect them along the z-axis. These layers allow the model to reference adjacent frames while generating the current one. Temporal attention enables communication between frames, but it does not provide the rigid blueprint needed to lock the geometry in place. The final step in achieving temporal stability is hard conditioning, the engineering of a structural lock. This requires bypassing the semantic text encoder when making decisions about the subject structure. We provide the U-Net with rigorous spatial maps, such as depth data or canny edge detection layers. A depth map sequence acts as an unyielding cage. It wraps around the latent data points to define their permissible boundaries. The scattered data points are forced into a tight linear trajectory along the z-axis, significantly reducing variance. Instead of guessing geometry, the U-Net is now anchored to a consistent geometric grid across time. The diffusion process is then restricted to rendering texture, lighting, and style over that predefined geometry. Structural lock relieves the diffusion process of calculating 3D physics, moving the output toward repeatable geometric results. We can now see the visual result of applying a structural lock to the initial failure. The split screen highlights the difference. The unconstrained model on the left morphs, while the structurally locked model maintains perfect physical consistency across the sequence. The geometric grid ensures the subject's identity and volume remain intact from frame to frame. This level of control allows for frame-accurate editing and intentional motion. Mastering these constraints makes AI video a reliable component of a professional production pipeline. Effective AI video production requires a technical distinction between two types of control. Semantic text instructions are used exclusively to dictate surface texture and lighting style. Structural conditioning the blueprints and rulers of the process, dictates the physics, mass, and temporal trajectory. Attempting to solve geometric instability through text prompts ignores the underlying architectural reality of these models. Precision in AI video depends on the ability to engineer and manage the subject's latent trajectory. Moving to geometric constraint allows for the precise management of latent trajectories within the diffusion process.